Okay, you need to show, okay, show the energy profile diagram of an exothermic reaction. Reactants. Why did you put the reactants? Why did you put it here?
Because
Why did you put the reactant here?
the enthalpy of the product is less than the reactant. So
Yes, I know it's less than that, but you are fixing reactants almost similar to your activation energy. You remember this EA is activation energy, right?
yes.
Okay. I felt it should be something like this. Okay, let's get that now. Okay, so this is just it. For exothermic, we said the energy of the reactants is greater than that of the product. Okay, and if that's the case, the reactants will be here, the products will be here. Now, this gives us the activation energy, and this shows where heat is given out of the product. Do you understand that now?
Yes.
Okay, that's cool. Remember, we said that delta H is negative. Delta H is negative. All right, let me show you this video. I think I have to show you this video. Okay, come up, come up, come up, come up. All right, I guess we are here now. Are you seeing this? Can you see this?
Yes, sir.
Okay.
In today's video, we're going to look at what exothermic and endothermic reactions are, see how we can represent them using reaction profiles, and finally, consider the importance of activation energy. Now, the important concept to understand in this topic is that different chemicals store different amounts of energy in their bonds. For example, if we took the reaction methane plus oxygen to form carbon dioxide and water, then each of these different molecules would hold a different amount of energy. Or in other words, they'd each have different amounts of energy in their chemical energy stores. What's important to us, though, is how much energy all of the reactants have in total compared to how much energy all the products have in total. In this particular case, the products would have less energy than the reactants. And you can show this on a reaction profile, where the y-axis is the total energy of the molecule, and the x-axis is the progress of the reaction. So on the left, we place our reactants, and on the right, we put our products. But importantly, for this reaction, we'd have to put the products lower down, because they have less energy. Now, if the chemicals in the reaction have lost this much energy, then this much energy must have been released to the surroundings. Because remember, energy can't be created or destroyed. It can only be transferred from one place to another. And the most common way to exchange energy with the surroundings is in the form of heat. In this reaction, lots of heat energy would be released. So if we had done it in a sealed container, then we'd be able to measure the increase in temperature as the reaction progresses and releases heat energy. We call reactions like this exothermic. And what all exothermic reactions have in common is that they transfer energy to the surroundings, usually in the form of heat. The most common type of exothermic reaction is combustion reactions, in which fuels are burned, usually in the presence of oxygen, like in our reaction. Other examples, though, include neutralization reactions between acids and bases, and most oxidation reactions. The opposite of an exothermic reaction is an endothermic reaction. These are reactions which take in heat energy from the surroundings. For example, if we wanted to break down calcium carbonate into calcium oxide and carbon dioxide, we'd have to supply heat, perhaps by using a Bunsen burner to heat up the solid calcium carbonate. So if we wanted to draw a reaction profile for this reaction, then different reactants would be on the left and the products on the right. But this time the products would be higher up because they have more energy than the reactants. And so we'd label this difference as the energy absorbed rather than the energy released. So far, we've covered what exothermic and endothermic reactions are and looked at the reaction profiles which you might look for in the exams. The last thing we need to cover is activation energy, which is the minimum amount of energy the reactant particles need in order to collide with each other and react. So the greater the activation energy, the more energy that will be required to start the reaction. We can show this activation energy on our reaction profiles when we draw a curve from the reactants to the product to show how the energy changes during the reaction. Specifically, there's an increase in energy from the lowest energy level to the highest point of the curve is the activation energy. So as you can see, even in an exothermic reaction like this one, which releases energy overall, some energy is still required to get the reaction going in the first place. We can do the same thing for endothermic reaction profiles. Again, we draw a curve, and the activation energy will be the difference in energy between the reactant's energy level and the very top of our curve. This means that if we wanted to show the same reactions, but with slightly higher activation energies, then we just pick up the curve a bit higher. Whereas if we wanted to show lower activation energies, we'd just make them a bit lower. Now, the very last thing we need to say is that if you were drawing a reaction profile for a specific reaction, like the ones we discussed earlier, then instead of just writing reactants and products on the lines, we can actually put the chemicals from our equations. Anyway, that's all for now. So hope you enjoyed it.
Okay, awesome. Now, that was just a summary of what we just done. Okay, let's define some terms. Heat of formation. Formation. All right, what is the heat of formation? Right. The heat of formation of a compound is the heat change that occurs when one mole. The heat of formation is the heat change that occurs when one mole of a compound is formed from its elements. When one mole of a compound is formed from its elements in their standard state. In their standard state. The heat formation of a compound is the heat change that occurs when one mole of a compound is formed from its elements in their standard state. So what are the standard conditions? The standard conditions are for temperature, we have 25 degrees Celsius, that is room temperature. And for pressure, we have 1 atmosphere. 1 atmosphere. Okay, now what is the heat formation of water? Heat formation of water is minus 286 kilojoule per mole. Minus 286 kilojoule. Minus 286 kilojoule per mole. That means heat formation of water, we said it is minus 286 kilojoule per mole. That means what we are saying is the heat formation, that's H2 plus giving us, sorry, H2O. Now because of that, so we said the formation of that's heat formation of water is minus 280 kilojoule per mole. Now we have something. Now, if heat of formation is the heat change that occurs when one mole is formed from an element. Now let's talk about heat of combustion. Heat of combustion. This is the heat involved. This is involved when one mole of a substance is completely burnt in oxygen. When one mole of a substance is completely burnt in oxygen under standard conditions. Under standard conditions. Okay. The heat combustion of carbon is minus 393 kilojoule per mole. Minus 393 kilojoule per mole. All right. Let's just, I think there's a question here for us to solve. Calculate the heat of reaction in the equation. Calculate the heat of reaction in the equation below, given that the heat of combustion of carbon and hydrogen are minus 393 kilojoule per mole and minus 280 kilojoule per mole respectively. Have you seen that?
Yeah.
Okay. Then we have a. Let me get the question out again. And heat of formation of butane is minus 125 kilojoule per mole. And the heat of formation of butane is minus 125 kilojoule per mole. All right. All right. Now the heat of reaction is because these were the heat of reaction here will be quite easy because we are talking about. Remember, at this stage we are talking about exothermic reaction. Why are we talking about it? Why do you think we are talking about exothermic reaction? Let me ask the question here. I said, look at this thing here. From what we have done so far, I gave you the heat of formation and combustion of element. I wanted to ask you, or I was asking you, I was asking you that are they in were we talking about, are we talking about endothermic or exothermic reaction? Will it be endothermic reaction or will it be exothermic reaction?
Exothermic.
Sorry?
Exothermic.
Why did you say exothermic? Yep.
Because
You said?
because the product has
So I didn't get that. You said what?
because the product has less power than
Because the product has,
yes,
so did you say the product has hands?
less power than the reactants.
Okay. Yeah, because the product, and you see also not because of that, that's not the only one. You can see that it was also negative. The heat of formation or combustion of the elements there are also negative. All right. You saw it
Yes.
there that they were negative. So that's another reason. That's another reason why what we are talking about is a negative. They actually be a negative of that's exothermic reaction. Now, if that's the case, I want you now to look. What is the formula for exothermic reaction? What did we use as a formula for exothermic reaction? What did we use as a formula for exothermic reaction?
Exothermic.
Sorry? Now we've established the fact that that is an exothermic reaction. So if we have established the fact that that's an exothermic reaction, so then what if we have established that fact? So how do we then know, since we have established that fact that that's an exothermic reaction, how do we then know which formula to use? You remember I gave a formula for exothermic and endothermic reaction.
I give for only endothermic.
Sorry?
Give for only endothermic.
Endothermic, really? What's the formula I give for exothermic, please? For endothermic.
Sigma HP minus sigma HR.
HP. Sorry, please say that again.
Sigma HP minus sigma HR.
Okay. If I give you for endothermic, okay, then give me for exothermic. You should be able to know for exothermic then. I'm sorry I didn't give you that. I thought I did.
Sigma HR minus sigma HP.
Good. So that means you already know the formula on your own that it's you already know the formula on your own that that's sigma HR. Now, sigma HR minus sigma HP. Now, that sigma means that it's the sum of each, the sum of each of the heat, either heat of formation or heat of combustion. So, can you find your way around it now? remember what we're given was, let me get out. We're giving heat of combustion of C of hydrogen. Sorry, was it hydrogen? Coming, let me get that. We're giving heat of combustion of carbon, and height, that's minus 393 of carbon, minus 393 kilojoule per mole. Okay. The other one is the heat of combustion of hydrogen. That's hydrogen is minus 298, right? Was it 298? Let me get it. Okay, 286 kilojoule per mole. And then we had one extra, the heat of formation of butane, which is minus 125. Of butane, which is minus 125 kilojoule per mole. Now, one of the things we know then is this, that the delta H, irrespective of it, whether it's endothermic or exothermic reaction, is still the same formula of HP, sigma HP minus sigma HR. Now, let me explain this so that you know what to do from here. Now, what this means is sigma HP has to do with the summation of whatever heat, either the heat of formation or the heat of that's either the summation of the heat in the product, the summation of all the heat we are talking in the product, either the heat of combustion or the heat of formation. Because what they asked us to find was the heat of the reaction, which is delta H. And when they say sigma HP, that means we're trying to talk about the summation of the whatever heat, either heat of combustion or heat of formation. Actually, the heat of formation will actually be in the reactant, because we are talking about heat of formation of butane. Remember what we said as a definition of heat of formation. I did mention that heat of formation is the heat change that occurs when one mole of a compound is formed from its elements in their standard state. So before they are being formed, now the heat of formation, now they gave us for butane. And where is butane? Butane is at the reactant area. So that means this heat of formation will be for the reactant butane. This is butane. Now, and they gave us the heat of combustion. Now, this is a combustion reaction because it reacts with oxygen. Now, they gave us the heat of combustion of carbon here and the heat of combustion of hydrogen here. Now, this HP, now I'm going to repeat it again. What I said was this. I said, when we're talking about the heat of reaction, we have the heat of reaction, which is delta H, which is the sum of the heat of the product minus the sum of the heat of the reactant. Now, they gave us the heat of the heat of combustion of carbon, heat of combustion of hydrogen, and heat of formation of butane. Now, what heat of these products mean? When they say summation, that means it is the sum of whatever heat they gave you in the product. Now, the sum of whatever thing they gave you in the product. In this case, which is the heat of combustion. Remember, this is combustion. Now, we are talking about combustion. That we are talking about the product formed in combustion. Because when we talked about combustion, we did mention that the heat of combustion, when we're talking about combustion, we said the heat of combustion is the heat evoked when 1 mole of the substance is completely burnt. Now, carbon from butane was completely burnt to give us, remember we're talking about 1 mole. Now that gives us CO2, carbon here, and then hydrogen here. So the heat of combustion in this case now, it will be in the product because it has to do with combustion where it has been burnt and it is now formed. Where it has been burnt in oxygen. So this will be in the product. Now this summation means it will be the sum of whatever heat you were given in the product minus the heat of formation. Now, where is butane? We all know that butane is in the reactant part, not in the product. Butane is in the reactant part. So this becomes minus the summation of the heat of formation of butane in the reactant part. Now, when we subtract them together, that gives us the delta H, the heat of reaction. Do you understand that analogy, please?
Reaction is the heat of formation.
No. The heat of the reaction now, the heat of the reaction is the sum of heat, that's the heat of the products, minus the sum of the heat of the reactants. So it is now your job to know. When we now talk about the heat of the products, now, when we talk about the heat of the product in this case will become the sum of the heat of combustion of carbon plus the sum of the heat of combustion of hydrogen. Now, when we talk about HR will be the sum of the heat of formation of whatever thing you were given plus whatever, if you were given any other heat again, then you add them together. Then you come here to subtract them. Then the delta H becomes HP minus HR. Okay, do you understand what I mean now?
Yes.
Okay. Sorry, are you done?
Yes, sir.
Okay. Awesome. Correct. All right. Now, we should note this thing, that the enthalpy change of formation of an element. The enthalpy of formation of an element is 0. The enthalpy of formation of an element is 0. Just take that as a note. All right. Before we end this, I think there's one more thing I need to show you. One more thing we need to see. It would be nice if you don't see that either. Okay. How to calculate? Okay. Where are you? Okay, I guess you can see this, right? Can you see this? Hello?
Yes, sir.
Okay.
Yes, sir.
In today's video, we're going to see how we can use graphs to measure the mean rate of a reaction and the rate of reaction at a specific time. We saw in the previous video that we can calculate the rate of reaction by dividing either the amount of reactant used or the amount of product formed over the time taken for that change to occur. For example, if this reaction between magnesium and hydrochloric acid produced 1200 centimeters cubed of hydrogen in 4 minutes, then our rate would be equal to 1200 over 4 times 60.
I hope you understand this because we are trying to calculate the rate of reaction now. Remember, the rate of reaction formula is the amount of reactants used divided by the time taken.
Or 240.
Yes.
So it would be 5 centimeters cubed per second. The problem with this type of calculation, though, is that it only gives us the average rate during those 4 minutes. Whereas in reality, the reaction would have been fastest at the beginning, and then it would have slowed down as the reaction progressed. And by 4 minutes, it might have even finished. If we had a way to monitor how much gas was being released during the reaction, though, then we could plot it on a graph and see how the rate of reaction changes during the reaction. On the x-axis, we'd have time, and on the y-axis, we'd have the volume of hydrogen produced. At first, because there'll be loads of magnesium and acid that can react together, loads of hydrogen will be produced. So we get a very steep curve, which indicates a high rate of reaction. As the magnesium starts to get used up, though, the hydrogen will be produced more slowly, until finally the graph plateaus, once all of the magnesium has been used up. With a graph like this, there are two main things that you could be asked to do. One is to calculate the mean rate of the reaction over a certain period, which is what we did earlier. For example, what is the mean rate of reaction in the first 3 minutes? For this, we just need to use our graph to find out how much hydrogen was produced in those first 3 minutes. So we find 3 minutes on the x-axis, and then draw up a dashed line to see where it intersects our curve. Then we draw another line from this point across to the y-axis to find that 1200 centimeters cubed of hydrogen was produced. So we just do 1200 centimeters cubed divided by 3 minutes, or 180 seconds, to get an average rate of 6.67 centimeters cubed per second. The other thing you could be asked, though, is to calculate the actual rate at a particular time. For example, what is the rate of reaction at 2 minutes? To do this, we need to calculate the gradient of the curve at that particular point. So the first step is still to find 2 minutes on the x-axis and trace up to find where it intersects our curve. But then, instead of drawing a line across to the y-axis like we did before, we instead draw a tangent to the curve at that point. And remember, a tangent is just a straight line that just touches the curve and has the same gradient as the curve does at that point. Once we have our tangents drawn, we need to find the gradient of the line, which is equal to the change in y divided by the change in x, which in our case would be the change in the volume of hydrogen divided by the change in the time. The best way to do this is to make your line as long as possible so that it hits one of the axes. And then trace lines from the other end of your tangent to the y-axis and then to the x-axis. So now this section here would be the change in the hydrogen, which is about 600, and this section here would be the change in time, which is about 2 minutes 50 seconds, or 170 seconds. So we just do 600 divided by 170 to give us 3.53 centimeters cubed per second as our rate.
Did you get that? Did you get
Yes,
that?
sir.
Okay, have you, I hope you are drawing these things also.
Yes.
Just in case you're worrying about your tangents, the examiners know that you're judging it by eye, so they'll allow answers within a small range of values. So even though you should be careful and try to get as close as you can, you don't have to worry about getting it perfect. Before we finish, I just want to point out that we could also have done the same thing with a graph that plotted the amount of magnesium remaining against time. This time though, the graph would have started with however many grams we used in our reaction, so in this case 1.2 grams, and then would have declined rapidly at first, but then more slowly. So if we wanted to find the rate of reaction at 1 minute, we'd just do the same process as before. So we'd find the 1 minute point on our curve, draw our tangent at that point, and use that line to figure out our change in y, which is about 0.72 grams, and our change in x, which is 1 minute 40 seconds. And finally, we divide our change in y by our change in x.
I hope you know they're getting this change in y and change in x.
No.
Okay. Now this is how you did it. Now this is exactly what you did here. Around this place here, you should be able to know the. Now this is from 0 to 0.4. From 0 to 0.4, that means 0.4. That means each line here, this is about 10 lines. I get these are 10 lines since the gap is a bit wide. Now that means each of them here is 0.4. 0.4 plus, 0.04. Now if this is 0.04, another part is 0.08, another part is 0.012, another part is 0.06, 0.16, and then 0.2, 0.24. I feel this might be 5. Okay, let's use it as 5 because that looks a bit small. Okay, that means each line, let's say each line is 0.08. If this is 0.08, another line will be 0.16. Another line will be 0.24. Another one will be 0.32. 0.32. Then, if this is 0.32, sorry, 0.32 was not 0.32. Then after 0.32, the next one is 0.4. But do you understand how I got these values inside? Eh?
No.
Okay, good. This is how to do it in any graph. If you have something like this, if you have any graph like this, this is how to get the values inside. It's very simple. Just take the highest one. You can either take this or this, 1.2 minus 0.8, or you can say 0.8 minus 0.4. You can say 0.4 minus 0. So all you just need to do is put 0.4 minus 0 to get what each line, a graph has different lines here, right? You have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's if it is 5, that means we call that 1 unit or one unit, yes, which is 5 lines, but 2 units is 10 lines. So now this is 0.4 divided by, I guess this is 5 units. Why this is 5. Now, use your calculator and do this. 0.4 divided by 5. That would
0.08.
Sorry? 0.08. Good.
0.08.
Now this is 0.08. That means each line here is 0.08. Each line is 0.8. Now, if this is 0.08, add another 0.08 to give you 0.16. Add another 0.08 to give you 0.24. Add another 0.08 to give you 0.32. All right? Add another 0.08 to give you 0.4. Add another 0.08 to give you 0.48. Do you understand what I'm doing? Eh?
Yes.
Okay. Now, from
Yes,
here, now
sir.
this will give us 0.88. Now, how do we get the change in y now? The change in y becomes 0. You know, remember for us to get gradient, when we did physics the first time, that would be y2 minus y1, okay, over x2 minus x1. Okay, that becomes 0.88 minus 0.88 minus, let's see, 0.16 here, minus 0.16 divided by, okay, this is, now, can you tell me what each line here will be now? Can you tell me what each line here will be? For this one, let's use 5 here, 5 here. Let's use the lines are 1, 2, 3, 4, 5. So can you tell me what each line will be now?
0.2.
Good, 0.2. Okay, now if this is 0.2, that means this will be 1.8. This will be 1.8 here, right? That'll be 1.8 minus 0. So you now have to convert it to seconds now. Now that's how they got 1 minute 40 seconds. Then convert everything to seconds. All right. So do you understand how it's being done now?
Yes.
Okay. Now, okay, you see, if we use 0.88 minus 0.16, it's going to give us 0.72. 0.88 minus 0.16, it still gives us 0.72. All right, let's continue, please. Let me clear this first.
So 0.72 divided by 1 minute 40, or 100 seconds.
You understand how I converted it to seconds, right?
So, but there was no change in x. Oh, using 1.8.
Yes, that's because of here is 0 now.
Okay.
Do you understand?
Yes, sir.
X2, why this one is 0, x1, right?
Yes.
Okay. So that this is x2, this is x1, so that's why. All right.
Find our rate of 0.0072 grams per second.
But you understand how you got this 100 seconds, right?
Yes.
Okay.
And if you make your tangent a bit longer or a bit shorter, and to use different y and x values, that's absolutely fine. As long as your tangent is just as steep as ours, you would end up getting the same answer.
All right.
Anyway, that's all for today.
Okay,
If you enjoyed it, then please do give us a like.
So that's the explanation of how we do to calculate the rate of reaction. All right. Time is almost fast spent. Let me see assignments to give you. The next time we'll be talking about chemical equilibrium. That's where we have to talk about Le Chatelier's principle that I gave you before. And don't worry, I think I'll have to look out for, I'll have to give you your assignment. I'll send it to mommy then, if that's the case. I'll send it to you. Oh, sorry, I think, don't worry, I'm going to send it to you. All right?
Okay.
So any other question? Any question, please?
No.
All right. Let's pray then. Father, I thank you for today. Thank you for your mercies. Thank you for helping us today. Thank you for your love. Blessed be your holy name in Jesus' name. In Jesus' name, we prayed. Okay.
Amen.
Like I said, the next time we meeting up, we're looking at chemical equilibrium. We are already done with this topic. So, but the assignment I will give now will help us know if we can continue with chemical equilibrium, which is quite easy. All right. Have a wonderful time.